잘 나오네. 여기서는 잘 나오네. 오케이.
Yeah, it was
아직
very.
원래 Okay, so thanks for coming. So today we have Ilkyoo Choi from Hankuk University of Foreign Studies. Also, he's a new member of Discrete math group from this year, and he will talk about DP coloring, right? Please.
Okay. Thank you for the introduction. Thank you for the invitation to give a talk. It's always good to be back in Daejeon. So today I'll be talking about densities of list critical graphs, but based on DP coloring. So I'm always afraid of 15-minute long talks. So please, if you have any questions, just raise your hand and ask a question. So this talk will be more about the history and some results, and it will be more like a survey than proofs and like the new results, because it's hard to fill up 15 minutes. Okay. So this is joint work with my advisor Sasha Kostochka, his postdoc Peter Bradshaw, and Jingwei Xu, who is a Sasha student. So this is work I did last year when I went on sabbatical. Okay. So I'm sure you guys all know the definition of proper coloring, but yeah, so this is the definition of proper coloring. So usually we're interested in these obstructions, right? So if your graph has chromatic number k, that means you can't color it with k-1 colors. And what are the obvious obstructions? So the first one, of course, is the complete graph. If you have a complete graph, then all k vertices must be colored differently. So if you have complete graph on k vertices, then your chromatic number is at least k. But in some sense, this obstruction is very dense. It's a dense obstruction, but also it's very it's a minimal obstruction, right? Because if you remove any edge, then the chromatic number drops. In particular, this graph here, which is K4, if I remove any edge, the chromatic number will drop from 4 to 3. Right? But then there are other graphs that are, in some sense, minimal, something like this, which is like one of the 4 order graphs. Right? So this graph also has chromatic number 4, and if you remove any edge, the chromatic number will drop from 4 to 3. So these are some obstructions for graphs to be 3-colored. Right? You want to color your graph with 3 colors, but if you contain one of these graphs as a subgraph, then you can't do it. And so we're interested in finding these graphs. Right? So these graphs are called k-critical graphs. Right? So these are graphs where the chromatic number is k, but if you remove any edge, so if you look at any particular subgraph, proper subgraph, then the chromatic number becomes at most k-1. Well, actually it becomes k-1 because you removed one edge. So in some sense, these are the minimal graphs where you cannot color it with k-1 colors. They're called k-critical because the chromatic number is k, but you should think of it as obstructions for graphs for being a k-1 color. So one observation is that if your graph has chromatic number at least k, then you will have to contain one of these k-critical graphs as a subgraph. Right? And why is that? Well, your graph has high chromatic number, at least k, and you will remove an edge one by one. Right? And after each edge removal, your chromatic number may drop or not. But at the very end, if you finish removing all the edges, the chromatic number will be 1, right? Because you're left with an independent set. So at some point, your chromatic number has crossed the boundary, right? At some point, the chromatic number dropped from k to k-1, and the graph where the graph right before it dropped will be your k-critical subgraph. So what are we interested in? We're interested in the density of these k-critical subgraphs. So in particular, if you look at these 2 graphs with my fancy laser pointer, the one on the left has density 3, right? The average degree is 3. And the one on the right, this one has average degree 3 plus some epsilon, right? Because there's only one vertex of degree 4 and everything else is degree 3. So the densities are different, but the one on the right has more vertices, right? So it's on a larger vertex set. So the goal for this talk, or the goal of the topic, is figuring out the densities of these critical graphs. And when k is at most 3, this is very easy, right? Because when k equals 1, this is the one critical graph, and there's only one such graph, which is a single vertex. When k is 2, you're looking for 2 critical graphs, and again, there's also only one such graph, which is an edge, right? The complete graph on 2 vertices. And when k equals 3, you have all these odd cycles, right? The odd cycles have chromatic number 3. Once you remove an edge, it becomes a path which is chromatic number 2. Right? And there are no other 3 critical graphs. Okay. So from now on, we're going to assume k is at least 4, right? So you have at least 4 colors. And we're going to define this function which is f of n comma k. So this is the minimum number of edges in a k-critical graph on n vertices. And of course, n has to be at least k, because if you have less than k vertices, then your chromatic number will never be k. You can just give them all different colors. Okay? So whenever you see n, it's at least k, and whenever you see k, it's at least 4. And I know I said I'm going to keep using the word density, but this function is in terms of the number of edges, but they're the same, right? I mean, you can translate one from the other too very easily. And then these are some very basic facts. Right? So the first one is when n is as small as possible, namely k, then it's k choose 2, right? Because if you're a graph on k vertices, and if your chromatic number is k, then you have to be the complete graph. And coincidentally, this complete graph is critical, because if you remove any edge, the chromatic number will drop. But also, for the next value of n, when n becomes k plus 1, then we know that no such k-critical graph exists. And this follows from a very simple structure theorem, which I will show in the next slide. So one of the first facts you know when you study these k-critical graphs is the minimum degree must be k minus 1. Right? And why? Well, this is also very simple. Right? Here's the proof. Right? You have some graph, which is k-critical, and if you have a vertex of low degree, which is degree k minus 2, at most k minus 2, I just remove that vertex, and because what's left is a subgraph, the chromatic number will be at most k minus 1, because your graph is k-critical. And you try to extend the coloring to the vertex you removed, and because this vertex only has k minus 2 neighbors, and if you have k minus 1 colors, there's a leftover color you can apply on this vertex that you've removed. Which means your entire graph was k minus 1 colorable, which is a contradiction, right? Because your graph is k-critical, meaning the chromatic number must have been k. So what this is saying, if you give me a k-critical graph, there's a lower bound on the minimum degree, or there's a lower bound on the vertex degrees. And because of this, we obtain this very simple inequality. Right? Remember, this is the number of edges in a k-critical graph on n vertices. And if every vertex has degree at least k minus 1, then every edge gets counted twice. So that's why we have n over 2. But actually, when Dirac proved this lemma, or when he put this statement out, he proved a little bit more. He said you could do slightly better, right? You can add something like k over 2 more edges to this k-critical graph. So this is very simple. And as I was saying on the first slide, f of k comma k is k choose 2, the complete graph. And using this theorem or this lemma by Dirac, we can prove that there's no k-critical graphs on k plus 1 vertices. And this is also very simple. How? Well, if you're a graph on k plus 1 vertices, there has to be a non-edge, right? Because if all the pairs are edges, that means you're a complete graph on k plus 2 vertices, which doesn't make sense because your chromatic number is k. So here's your non-edge. And because you're a graph on k plus 1 vertices, all the remaining vertices are here somewhere, right? But now you look at this lemma, which says if you're k-critical, then the minimum degree is k minus 1, which means x and y are joined to all the other vertices. So it's you have all the edges possible between these two blocks. So now you gain some structure, and using this structure, you can conclude that this graph doesn't exist. How? Because I'll just ignore x. If I ignore x, it becomes a subgraph, which means the chromatic number is at most k minus 1. So I can color it with k minus 1 colors, and then I can copy the color on y onto x, because they have the same neighborhood. Now this means the entire graph, I've colored it with k minus 1 colors, which is a contradiction, because my graph was supposed to have chromatic number k. So what this is saying that these graphs don't exist. So on k plus 1 vertices, you don't have a k-critical graph. And this is due to this easy observation, which I'll call a structure theorem. But I can go further, right? I can go on to k plus 2. So now you have k plus 2 vertices, and you want a k-critical graph, and you can do some similar arguments, and you can conclude that your graph looks like this. What's this? This is a complete graph where a phi cycle is missing. Right? So I phrase it like I drew this picture saying you have a phi cycle on the left, and on the right you have all the other vertices, k minus 3, because your entire graph has k plus 1 vertices. And then I have all edges possible between the two blocks. But if you look at it as a whole, you're just missing the edges in the complement of this phi cycle, which is a phi cycle. Okay? And if you count the number of edges, you get k plus 2 choose 2 minus 5. Okay? So there's actually a unique graph, a unique k-critical graph on k plus 2 vertices. Okay? But you can go further, right? You can go k plus, when n is k plus 3, k plus 4, keep going. And this is exactly what Gallai did in 1963. So he said, okay, if you're a k-critical graph, and if you don't have too many vertices, at most 2k minus 1, then the complement is disconnected. Right? So if the complement is disconnected, it gives you this structure that I showed you before. It gives you this, right? It's because the complement is disconnected, it's just saying in the primal graph, in the original graph, it's a join between two blobs. And using this, Gallai was able to prove that, he was actually able to compute the exact value of this f of n comma k. Right? Because you know the structure, you can count the number of edges. Right? And if you look here, this is k minus 1 times n over 2, which is the bound you get from Dirac. And then you have something that involves both n and k, just to show that this is a better bound than Dirac's bound. Okay. But of course, you want to do something more general, because this has the catch here is you don't have too many vertices. So in general, what Gallai proved is that if you're a k-critical graph, and if you look at the vertices of minimum degree, and because the minimum degree is k minus 1 by this lemma by Dirac, he said, okay, if you're a k-critical graph, you look at all the vertices with lowest possible degree, then it will be a Gallai forced. And what's this Gallai forced? It's it's written there. It's a graph where each block is a complete graph for an odd cycle, and it looks like this. It's just so it basically looks like a tree where if you look at the components that don't have if you look at the blocks which are what are they? Maximal two connected subgraphs, then either they're an odd cycle or they're a complete graph. So the catch is we know the structure of these minimum degree vertices. And from this, you should be able to calculate some densities. Right? So Gallai actually proved this. Right? So using this, he said, okay, he actually improved the coefficient on n. Right? So coefficient of n over 2 used to be k minus 1, but now he said k minus 1 plus something that is asymptotically 1 over k. But not only he proved this structure theorem, he made a conjecture. He said, okay, if the minimum degree vertices, if they form a Gallai forced, what's the worst case? The worst case is probably you have this Gallai forced with one extra vertex, where the extra vertex is connected to this Gallai forced in a certain way. So he proposed some structure. He said, okay, this will be the worst case. And he made this bold conjecture, where he said, okay, because you have this certain structure, he had to have some limitation on this number of vertices. So if the number of vertices is 1 mod k minus 1, then the minimum number of edges in the k-critical graph will follow this formula. And then a couple years later, Oren looked at this conjecture, and then he generalized it. Right? So he said, okay, it's phrased differently, but it's the same thing. Well, it's a generalization, because Gallai's conjecture is only for n when n is 1 mod k minus 1, and Oren's conjecture is for all n at least k plus 2. He said, okay, if you start with a k-critical graph with the minimum number of edges, and if you add k minus 1 vertices, then you will add exactly this many edges. So he made this conjecture, and he had a reason, right? And the reason was he had a different construction. Right? So this is the conjecture, And the construction is probably what you guys all know from graph theory. It's okay, you have two complete graphs, or you have two graphs, and on the left, on the right you pick an edge, which you will delete eventually, and on the left you pick a vertex and you look at all the incident edges. And what I'll do is I'll remove the red edge on the right and the left vertex on the left, the right vertex on the red vertex on the left. But instead of deleting all the blue incident edges, I will connect the blue edges to the endpoints of the red edge on the right. So it will look something like this. Not necessarily 2, 2, but maybe 1, 3, right? But not 4, 0. Right? Yeah, you want to keep it 2 connected. So this was his reasoning, and this is a very well-known construction. It was used by Dirac, Gallai, Hayoshi, and Ore, and but we give it this name. We call it the K-Ore graph. And his conjecture was, if you start with lots of these complete graphs on K vertices, and you keep doing these DGHO decompositions, so you keep combining these complete graphs, or even the complete graph and some other graph. So if you keep combining them until they're connected, then you will still have a K-critical graph. And if you count the number of edges, they will follow exactly this formula on the top. So he had his reasons. So what's known about this conjecture? Of course, we have these bounds by Dirac and Gallai, but then Krivellevich and Kostochka and Stevitz improved these bounds. So so Gallai, so Dirac did k-1, and Gallai did k-1 plus something that's asymptotically 1 over k. Krivellevich also did something that's 1 over k, but it's a better 1 over k because the denominator is smaller. And then Kostochka and Stevitz improved this to something asymptotically 2 over k. Yeah, so they're getting closer and closer. Until, actually, I was a grad student, and Sasha and Matt Yancey actually proved this conjecture. Right? They said, okay, this conjecture by Gallai is true. Right? And they proved something that's between Gallai's conjecture and Ore's conjecture. So they proved Gallai's conjecture, and then they also proved Ore's conjecture for every value of k, and n and k, except for some finitely many values of n, depending on the value of k. So Ore's conjecture is almost true. This is actually the title of their paper. And because of this statement, they have this statement, and they were also able to prove Ore's conjecture when k is exactly 4, or when k is 5 and a certain parity of the number of vertices. And then they worked on this even more, and what they were able to prove was they actually determined all extremal examples for their bound. Right? And it turns out all the extremal examples are exactly these k-order graphs that we saw on the same slide, but when I was explaining the motivation behind Ore's conjecture. And then in this process, so this is some 45-page long paper, and in this paper they proved they showed Ore's conjecture holds for more of these values of k and more of these values of n. Okay.
But they didn't disprove the conjecture.
No. So Gallai's conjecture is true because Gallai only conjectured it for when n is 1 mod k minus 3, and then they proved Ore's conjecture, almost Ore's conjecture. Right? So they proved the bound, but for certain values of n and k, but all values except some finitely many values of n depending on k. So if you give me a k, it's true for almost all values of n except k cubed values of n. Any other questions?
But those values, do they have upper bound?
Do they have an upper bound?
For any k,
I don't think so. So it grows with k.
It grows, but still, for each k, they have some function where I can compute. And
I don't think so. Probably not. Okay, so this is the state of the art for Ore and Gallai's conjecture. So what do you do after you see this? Of course, you try this for list coloring, which is a generalization of proper coloring. So Wiesing and Erdős, Rubin, and Taylor introduced list coloring. And this is the definition, which I'm sure most people here know. So, but I'll go through an example, right? So you have this graph K24. So of course it's a bipartite graph. You can properly two-color it this way. But it's not two-list colorable, which means I will guarantee two colors on each of the vertices, but the colors you guarantee on the vertices might be different. So here, on the left, you have red and blue, and on the right, you have what? Orange and green, right? So if you try to color the vertices from your lists, from the available colors, then you won't be able to finish the coloring. Because for every combination of a color on the left and a color on the right, there will exist some vertex in the middle whose list is exactly the two colors you've chosen for the left and the right vertex. Right? Which means guaranteeing two colors for this graph is not enough. Right? So the list chromatic number for this graph is more than 2, so at least 3. Okay? So the list chromatic number is harder than the chromatic number. And we can do the same thing, right? We can define these list critical graphs. Right? So what does this mean? This means your graph has list chromatic number k, but if you remove any edge, if you look at any proper subgraph, then the list chromatic number will drop from k to k minus 1. Right? And then you can do the entire story. Right? Now I define this function f sub L of n comma k, which is the minimum number of edges in your graph, which is list k critical. Okay. All right, and then I'm going to do a story again. So Dirac's bound holds, right? Because it had nothing to do with the colors. You only counted the number of neighbors, so you still have this many edges. But then here, the story for Gallai changes a little bit. Remember, for Gallai, we said if you look at the vertices who have minimum degree, then it forms a Gallai forest. But here, instead of looking at the vertices of minimum degree, we have a different structure theorem, which says that it actually characterizes when a list assignment is not fulfilled. Namely, if you give me some list assignment, I'll say, well, it's not colorable if you're this graph. So we say, so a degree list assignment is I will guarantee some number of colors for every vertex, but the number of colors I guarantee for that vertex will depend on its degree. So here, that's what this is saying. The size of the list, the available colors for that vertex u, is at least its degree. And if I give this degree list assignment to a graph, and if you can't color this graph from these lists, then you know exactly how the graph looks like. And coincidentally, it's the same graph that we saw before. It's the Gallai force. So using this structure theorem, you can obtain the same bound, right? Because the structure is the same. So he proves, so Gallai, well, he didn't prove this because he was before list coloring was invented. But using the same arguments, because we know the density of these Gallai force, he said the minimum number of edges satisfies this equation, which is the same for proper color. And then there's some improvements among these numbers, improving the coefficients and adding some larger additive terms. Until Rayburn, he had the previous best result, and he actually proved it across 2 papers, where he said, okay, what's interesting here is he had different proof techniques depending on the number of colors. So if the number of colors was small, if it's 4 or 5, he was able to prove k minus 1 plus something that's asymptotically 1 over k. And when k is large, when at least 7, then he was able to push it even further by saying it's something k minus 1 plus something asymptotically 2 over k. So somehow, if you have fewer number of colors, it's harder. And it's harder to obtain a good bound because it's just harder to prove stuff because you have more exceptions. You have to deal with more cases. In other words, it's easier to construct graphs that are not k-list colorable when k is small opposed to when k is big. Okay? And this is all that was known for list coloring. So what did we do? My advisor likes DP coloring. So this concept of DP coloring, which is also called correspondence coloring, was recently invented less than 10 years ago. And this is the definition, which is very scary, but I'll show pictures instead. So this is a picture. So the thing on the left is your graph. It's a 4-cycle. And the thing on the right is the cover graph. So you should think of this as the G is your graph, and H is the collection of the available colors of the vertices of G. And now if you're doing list coloring, what you're trying to do is you're trying to pick a color for each vertex from its list of available colors. But you want to do it under the assumption that adjacent vertices don't receive the same color. So if you think of H as some sort of conflict graph, I should put edges in like this. What this is saying is I can't choose, if I choose red here, I can't choose red and red here, right? Because they're the same colors. And if I choose blue here, then I can't choose blue or blue here. So H is just the conflict graph of the colors of the available lists of the original graph. And what do you want to do? You want to pick a color from each of the available lists so that the colors you've chosen induce no edge. So for example, if I choose something like this, red for the top and bottom vertex and blue for the left and right vertex, then the chosen vertices will not induce any edge. So this is a good color. But the twist here is for correspondence coloring is I can put any matching between the list of available colors. So here, instead of putting red and blue, right, I can twist the matching between these two color blocks. So here, these three matchings are natural, but the last one has a twist in it. Right? And this is why it's called correspondence coloring. Right? I can redefine the correspondences between the colors and say, okay, between these two vertices, I don't want to allow the pair red and blue or blue and red. Right? Opposed to in traditional coloring, I only wanted to avoid monochromatic edges. So this is like a small twist. And once you allow this, then you can't complete the coloring. Right? Or you can't pick a color from each of the color lists so that you will not induce an edge. Right? Like this, right? So if I choose red for the top, then of course because of these two edges, I have to choose blue and blue. Then if you look at the bottom vertex, there's no color I can choose because both of these are forbidden by this edge and this edge. So what this shows us is if there exists, this basically shows us that 2 colors is not enough for the C4. For a 4-cycle, guaranteeing 2 colors doesn't work in this setting of correspondence coloring. So this is a much stronger coloring than list coloring. So why do people investigate this? It's similar to why people investigate list coloring. So what's the motivation behind list coloring? So in proper coloring, if you pre-color some of the vertices, and if you remove that set, if you look at what's remaining, then the remaining vertices might have different lists, right? Depending on which of its neighbors were pre-colored with which of the colors. But if you want to do something like that in the setting of list coloring, you can't do that. Because, for example, when you try to contract a vertex or contract an edge, when you're contracting an edge, in the proper coloring setting, you just contract it and you still have the same set of k colors available for that vertex. But for list coloring, when you contract an edge, then the question becomes, what will be the list for this new vertex that you've created? But here in the DP coloring setting, if you have an edge, you can still contract it. Because now suddenly the colors, the color of the colors don't matter, right? It's just the ordering and how the matchings look like between the two neighbors you have. So now this will allow identification of vertices or contractions of edges. Right? So it's a harder coloring, but it makes your induction easier. And this is why people like correspondence coloring. Okay. All right, so even in this setting, we can define the same thing, right? We can define this thing called DPK critical graph. So this is where your graph has dp chromatic number k, but every proper subgraph, namely if you remove any edge, the dp chromatic number will decrease. Okay? And then we define this function, f of dp n comma k to be, it's the same story, right? Minimum number of edges in the n vertex dp k critical graph, but the catch here is it has to be a simple graph. Because another difference between dp coloring and the other proper or list coloring is that now suddenly multigraphs matter. So in the proper coloring setting or the list coloring setting, it didn't matter between a pair if you had two or more edges, right? Or one or more edges, right? Because as long as you have an edge, it will act as some restriction. Right? But here in dp coloring, if you had if the multiplicity between two vertices is k, or not k, but maybe m, then by definition, which I skipped, the definition says for every edge in your original graph, you will add a matching between the corresponding color pairs. Okay? So now if you have a multigraph, if you have a parallel edge between two vertices, then the definition says you will have to put two matchings. Okay? And the more matchings you put in, it will become more restrictive, right? Because in your cover graph, you will have more edges here. So for dp coloring, multigraphs is significantly different from simple graphs. But nonetheless, what's our goal? Our goal is to find this density for critical graphs for dp coloring. So we decided to use this definition for simple graphs. Okay, so I hope that makes sense. Right. And then the story repeats itself. So for proper coloring and list coloring, you have these structures. And of course, the minimum Direct bound of minimum degree at least k minus 1 also holds for dp coloring, because that's only about the number of neighbors. But here, we have to look at the lists and the matchings themselves, right? In the cover graph, how the matchings look like. So for list coloring, how Erdős, Rubin, and Taylor, they said if you give me a degree list assignment, then it's not that list colorable if it's a Gallai forest. Well, here something similar holds for dp coloring. We can define something like a degree cover, which means that the number of colors you have for that vertex is at least the degree of that vertex. This is the same. But because of this, basically because even cycles are also bad, right? In the previous slide, I said even cycles, you can't color it with 2 colors, you need to have 3 colors. Now suddenly, for dp coloring, you have more 3 critical graphs. Okay? Remember, in proper coloring and list coloring, the only 3 critical graphs were odd cycles. But now in the dp setting, even cycles also become 3 critical. Okay? So now we define this thing called a Gallai dp forest, short for GDP forest. So this is a graph where every block is a complete graph or just a cycle, opposed to an odd cycle. Right? So now we're allowing these blocks to be even cycles as well. Okay? And then in the seminal paper by Dvorak and Postel, they proved, well, they didn't state it explicitly, but if you read their proof, what they actually proved is if you give me some degree cover, where you guarantee the number of colors is at least a degree, no matter how the matching looks like, if the graph is not colorable, then it will look like this GDP forest. And the neat thing about this is odd cycles and even cycles have the same density, right? They're all 2 regular. So even though the definition of this bad situation, right? Gallai forests only have odd cycles as blocks, but now this GDP forest, they also have even cycles as bad blocks. Even though the structure is different, the densities are the same. So this Gallai bound from the 60s, of course, 55 years before dp coloring was invented, it still holds, right? Because once you compute the density of this Gallai forest, it also is the same for this GDP forest. Okay? And this was basically this was the only thing that was known for dp coloring, or the density of dpk critical graphs. So what do? We improve this. So what's this? So Bradshaw, myself, Sasha and Jingwei, what we proved is if you give me at least 5 colors, when k is at least 5, and then this is some lambda, where it's just some number, it's something like asymptotically k over 2. We proved that if you give me an n-vertex k-critical graph in the dp setting, and if you're simple, then either you're this complete graph, which is the obvious obstruction, or you have this many edges, where this is k minus 1 plus 1 over lambda. And because lambda was k over 2, this is something asymptotically 2 over k. Right, 2 over k. So we improve upon this this bound, right? Gallai's bound was 1 over k asymptotically, but now ours is 2 over k. But now you can ask, okay, this is for k at least 5, right? But we want to know what happens when k equals 4. Right? So for k equals 4, we also have some results. Right? So when k equals 4, we had to prove it separately, because simply for k equals 4, there's more exceptions. Right? Remember when I was talking about Landon Rayburn's result about list coloring, I said depending on the number of colors, he had different proofs. And that was because if the number of colors is small, then somehow you can make you have more bad graphs you have to avoid. And this phenomenon also showed up when you were doing DP coloring, the correspondence coloring. And the bad graphs are these 4 ore graphs, right? So of course a complete graph on 4 vertices is also 4 ore, but if you combine them, these are also all 4 ore graphs. So we proved that either you're a 4 ore graph on at most 10 vertices, so you start with 3 of these complete graphs on 4 vertices and then you combine them, or you have this density, which is what is it? It's like 3.2. So this says if your graph has more than 11 vertices, or at least 11 vertices, then you have this many edges. So these are our results for DP coloring. And because our results are for DP coloring can be used for a tool for list coloring as well. And all of our results also imply the same bound for list coloring. And this is not immediate, but we have to add like maybe half a page or maybe a full page proof explaining how to apply these results for list coloring. But anyway, we were able to do it. And if you compare these numbers to Rayburn's result, right? Remember I was saying our numbers were 2 over k, right? And this was also 2 over k, but our 2 over k is better because of constant. Right? So we slightly improve Rayburn's result. And right, so these are Rayburn's bounds, but we also, for the ease of the reader, right, we just plugged in numbers and showed them our bounds are bigger than Rayburn's numbers. Okay. All right. Okay. So that's that. Maybe I'll talk a little bit about the proof. So the proof uses the potential method, which is strengthening of discharging. So what's the potential method? The potential, for every vertex and edge, you will assign some weight. And when k equals 4, the weight is 8 and negative 5. And if you give me a graph, and if you give me a vertex subset, the weight of that subset will be just add up all the weights of the vertices and edges within that subset. Okay? And how do we get these numbers 8 and negative 5? Well, we had a goal, right? We wanted to show that the number of edges is this number times the number of vertices. So the denominator becomes the weight of the edge, and the numerator becomes the 8 of the vertex. So here it's 8 over 5, but if you look at our theorem, it says 16 over 5. But that's because here it's n over 2. Right? So we have this goal, we have this objective, and we define the weights like this. So if you just plug in the numbers and if you do the calculation, this is just saying the potential of the entire graph is negative. It's at most negative 1. And we use the fact that these weights are integers, right? Because the weight function is, you multiply some integers and you subtract some integers, so the result also has to be an integer. So we get some gap between the maximum average degree and these integers. Right? So anyway, our goal is to show that our minimum counter example is dense, right? Because we want some lower bound on the number of edges. But if you give me some counterexample, of course, this is a counterexample, so the conclusion shouldn't hold. So we start with a graph that's sparse. And then what do? We have this lemma, which we call a gap lemma. So what this is saying is if you give me a vertex subset, then I know the potential, well, I have a lower bound on the potential of this vertex subset. And if it's a lower bound, if the potential is high, if there's a lower bound, what that means is that part is very sparse. Right. I mean, the minimum counterexample, overall it's sparse. So if you look at every local part, it also has to be sparse. But there's a gap between this 0 and 2. So if the gap is bigger, then the proof is easier. And moreover, we were able to parameterize the potential of this vertex subset depending on the number of edges that leaves that vertex subset. So that's just some technicality. But anyway, how do we use this lemma? Well, using the lemma, we prove that, well, if you pick a vertex subset, then this vertex subset has to be sparse. But if it's sparse, it can't exist, right? Because if you have a sparse vertex subset, I will remove it, obtain some coloring by criticality, and then I can extend it with high probability because it's sparse. So if you look at the graph locally, it will not be sparse. So, yeah. So locally, the graph is not sparse, but globally, the graph is sparse. Right? So locally, it's not sparse, meaning locally it's dense. And then we use discharging, which is basically we will transfer the weights somehow according to some magical rules, and then we will recount the weights, and then suddenly the sum of the weights will be different, and then we get some contradiction. I know that was very hand-wavy, but trust me, the two papers together are 50 pages, and you don't want to go through it. All right, so this is the proof for k equals 4 when you have 4 colors. But if you want to extend this for more colors, you have to introduce more tricks. And these are the tricks we used. So first thing is we actually prove the statement for multigraphs, right? Because we want to do vertex contractions or edge contractions. When we contract a pair, that might create multiple edges, right? So we had to modify the proof for it to work for multigraphs. Second is we use variable list sizes. So of course, if we want to prove a graph is dp k-colorable, we give every vertex k colors. But because we wanted to use induction in various ways, we said, okay, maybe the list size is different for every vertex. So what that means is here, because k is 4, I had some fixed constant for this potential for a vertex. But here, because I have different list sizes for different vertices, I had to give different potentials for different vertices depending on its list size. And it was very hard to figure out which number or which weight to give to which list size. And then also the same deal for multiplicity. Here it's written that every edge gets potential -5 or 8 or weight -5. But if it's a single edge, we gave it some weight. But if it's a multi-edge, we didn't give twice that weight. We gave a little bit more of the negative weight just to make sure the induction works. And then we do the same thing as history tells us. We analyze the low degree vertices, and turns out these low degree vertices form a GDP forest, and it's a GDP forest with no complete graph of a certain size. Okay, all right, and I think that's it.
Thank you. Any questions?
Since you're an expert in AI now, discharging seems like something you could try to do with AI as well. Like,
yes.
You come up with the discharging rules. Like, have you thought about this? Or?
Yeah. So last year I was on sabbaticals, which meant I had too much time. So I looked into this machine learning and this reinforcement learning, and I used AI to reprove some known results. And right, for this framework of discharging, it works very well, because the discharging, it has two parts, right? First, you have to prove certain sparse configurations don't exist. Now this is the hard part. But for the discharging, where you come up with these rules, where you want to redistribute the weights, it's just an integer program. But, okay, so when humans try to make these integer programs, what do? You say, okay, if the vertex degree is high enough, then you just cut it there. You say, okay, if it's high enough, you treat them all the same. If the face lengths are, I mean, there's no faces here. But if the face length is long enough, then okay, you say, okay, that's good enough, it has enough charge. So I wrote a program that will figure out what the cutoff is, and also it will generate all the configurations you have to check. And I just feed that into an integer program and use Gurobi to solve the integer program. And what's great about this integer program is it will tell me how far away I am from the solution. And moreover, it will tell me which of these inequalities are tight, which means I just have to go look at that configuration and try to find reducible configurations near that inequality, or near that configuration corresponding to that inequality. So there was some success. The issue is trying to create these sparse configurations, right? So this, I think, because graph coloring is empty complete, it's not as easy as the other problems, but you can still do it. Because once you have a reducible configuration, it sticks. Right? It's not like you have to reprove it every single time. Right? So I was able to prove some toy problems, and there are a couple secret projects I'm working on. Yeah, so it works well. Or it works to a certain extent, is what I should say.
Is the bound type the theorem? I mean, you mentioned.
Good question.
Yeah.
So,
Like for infinite many values of n.
So when k equals 4, the bound is tight. So the coefficient is tight. So we phrased everything in terms of potentials. So if it's tight for potential, it's tight for max and average degree. But we weren't able to prove that the potential is tight, but we were able to prove that the max and average degree is tight for k equals 4. When k is bigger than 4, then it's we don't think it's tight. So basically, we came up with an example showing that this is tight. But we only realized that this example is that example after we submitted the paper. So.
How big is the gap between lower and upper bound?
Well,
the upper bound comes from the example, right? The lower bound
yes.
comes from the theorem.
So it's like it's like 2 over k. I mean the 2 over k because there's no conjecture. So I don't think it's too far off, but maybe I mean the Boreh's conjecture and Gallai's conjecture may still hold for DP coloring because there's no example showing that DP coloring and proper coloring are different for critical graphs.
And also you mentioned that DP coloring result gives you a corollary on list coloring. But this is not immediate from the statement, right?
No, it's not. Yeah, we have to do a little bit more work. Basically, just you give me a graph and you have these lists, and we modify it so it works for DP coloring, apply the theorem, and then we translate it back.
Oh, does that mean that you don't need to know the proof of the DP coloring result? Or
So if you give me a list k-critical graph, then I can modify it and give it some cover so that it works for DP coloring. And then I apply this theorem, I get some minimum number of edges, and then I translate that number of edges back here, and it will just translate back. Yeah.
Oh, I see.
So in some sense, translating a result from list coloring to DP coloring is easier than translating a result from proper coloring to list coloring, I think.
Any other questions? let's thank the